Okay, so now we are ready to present the Dijkstra algorithm. And let's first see it in action. So we are going to do this occupation or flooding process. And whenever we occupy a vertex, we're going to look on all the edges coming out of it to update the candidate values. So this is going to be 9, 6, 13. Then we occupy the one that have a minimum candidate value. You should think about all the other vertices, by the way, as having candidate value initially as infinity, right? Now we go over all the outgoing edges from the occupied vertex. We update the values. So, right, so this, for example, has 6 and 8. It's 14. 14 is not better than 13, so we don't update the candidate value. This is 6, but now we can compute the candidate values here and here, right, which we do. We get those candidate values. Now, again, we take the vertex outside the already flooded vertices and we take the minimum, we occupy it, and we repeat this process, right? And the important thing to observe is that the only vertices in the complement of X that get updated are vertices that are adjacent to the current vertex being handled. So as such, we don't need to inspect all the edges of the cut from X to the outside. We need only to inspect the edges adjacent to this just occupied vertex. And that would give us a big improvement in efficiency. Okay, and then to continue, and then we are done. Okay. So here's the new algorithm, right, where the main thing, it's as before. We take the vertex V that realizes the minimum candidate distance among all the vertices that are not assigned the distance yet. This is going to take us linear time if we implement it naively. And now we set the distance of this vertex to be the candidate distance. We add the vertex V to the set X. And now we have to update all the outgoing distances, but now we are doing it only for the edges outgoing from V, right? So for every vertex U, we look if there is an edge between V and U, and we update the candidate distance for that. Namely, we have to scan all the edges outgoing from V, so this is going to take the time proportional to the degree of V, right? Okay, so what is going to be the overall running time? Well, we have to do this of n step n times, so this is going to be of n square, right? The correctness, by the way, is already follows because this is just an instantiation of the basic algorithm, which already argued is correct. This step, this inner step here, for every backtest we have to play and pay its degree. Its degree, you know, every vertex pays its degree at most once, so it's a total sum of degrees, which means that it's of m. Another way of saying it is that every edge is going to be visited only one, because we're in a directed graph. So overall, the running time we are going to get is this. M plus n squared. Okay, this is of course silly because we are paying n squared for an operation which shouldn't be that expensive, right? Finding the vertex outside the current set, which is realizing the minimum candidate distance, we don't need to pay that much for it, right? We can do it more efficiently by using a data structure. So which data structure we are going to use? Well, we're going to use a priority queue, right? Now, you know, you don't really need to have this candidate distance where we are going to use just one array for distances. We don't need two arrays, so the code becomes a bit shorter, but it's the same thing. Now the priority queue, we're going to maintain all the vertices not yet occupied, and in every iteration of the outer loop, we're going to pick the minimum value stored in it, the vertex that is yet to be occupied, realizing the minimum value, and this is going to be the next vertex visited by this algorithm. Okay, so if we use regular queues, or regular heap, then every operation costs log n time. How many operations do we need to do? Well, we need to extract the mean here. This is extract mean, right? And here we update distances, right? For every vertex, for every edge in the graph, we check the new price, the new candidate price, and maybe this price decreased. And if it decreased, we need to reinsert it into the queue with the new price, right? So if you do it naively, that takes log n per edge. So overall, this is going to be n log n for this, because we do it n time, and log n per edge. So overall, we will get m plus n times log n. Now, there is a more clever data structure called Fibonacci heaps. You probably have not seen it. It's a bit more complicated. There are other data structure nowadays that support this operation in good time. So the basic idea is that extracting mean still costs you log n in those Fibonacci heaps, but decrease key, the operation of reducing a cost, costs you only constant. It takes only constant time. You have to be a bit more careful. It costs you constant time in amortized. Okay, so overall, overall the cost that you pay for decreased key over the m decreased key the algorithm does is O of m. So if you use this, then the running time of the Dijkstra improves to O of m plus n log n, which is that.